Section 9.3 is the complex plane and DeMoivre's theorem. So the complex plane is the cross of two axes, so like our rectangular axis here, where the x-axis represents the real axis or the real component of your complex number, and the y-axis represents the imaginary axis or the imaginary component of your complex number. So if you have a complex number, which we're going to call z, which is represented by x plus yi, I is our imaginary number I, then we can graph that point as x comma y, your real component, comma, your imaginary component. So for example, if I want to graph z equals root 3 minus I can plot the point root 3 comma negative 1, and that represents this z point. So try the next one. Plot the point z equals negative 1 plus I. So the first point here, root 3, negative 1, is down here. So then the next one, this is the same thing as negative 1 comma 1, because it's 1i. So I plot the point negative 1, 1. Try the next two, z equals 5 and z equals negative 2i. So z equals 5 means that there's only a real part, there's no imaginary part. So it's the same thing as 5 plus 0i, or the point 5, 0. So I plotted it out in the positive 5 direction and then nothing in the y direction. And then for the next one, same thing, 0 or negative 2i is the same thing as 0 minus 2i. So there's no real component, so it's just down 2 in the y direction. So if you have a point z equals x plus yi, we can graph it geometrically just using the real component on the x-axis and the imaginary component on the y-axis. The magnitude or the modulus of z, which we represent with these bars, kind of like absolute value bars, represents the distance from the origin to that point z in the complex plane. So if this is our point xy for z equals x plus yi, then the modulus or the magnitude would be this distance from the origin to that point. And then we can find that distance using distance formula or Pythagorean theorem, because you go out a horizontal distance of x and up a vertical distance of y, so you end up with the square root of x squared plus y squared, which is equal to r in our polar equations. So this modulus or the magnitude of z is the same thing as our radius in polar. It's also equal to the square root of z times z bar, where z bar is the conjugate of z. So if z is x plus yi, then z bar, or the conjugate of z, would be x minus yi. If you multiply z times z bar, this part that's underneath here, you would get x plus yi times x minus yi. So go ahead and pause the video and multiply these out. So if you multiply it all out, you end up with x squared minus xyi plus xyi minus y squared I squared. Well, the middle two terms are going to cancel each other out. And then just a reminder, I is the square root of negative 1, so I squared is negative 1. So you end up with negative y squared times negative 1, or positive y squared. So that's where the x squared plus y squared is. So your radius is the same thing as the square root of z times the conjugate of z. We can also look at polar forms of complex numbers. So if we have the rectangular form of a complex number to be z equals x plus yi, and we talked previously that x is equal to r cosine theta and y is equal to r sine theta, then we can convert this into polar form by replacing x and y with their corresponding polar forms. And so you end up with z is equal to r cosine theta plus r sine theta times I. And then the way that we normally write it is we factor out the r and write it as r times the quantity cosine theta plus I sine theta. The angle theta, whatever that is, we call that the argument of z. So use that information to convert z equals root 3 minus I into polar form, and also find the magnitude of z. So go ahead and pause the video and try that one. So I just converted root 3 minus I into just a point, root 3 negative 1, and we converted those into polar form in previous sections, so I just converted this into polar form. So I did Pythagorean theorem to find that the radius was going to be 2, and then I said that cosine of theta was equal to root 3 over 2, or x over r. And then we graphed this on the previous slide. I know that this is in the fourth quadrant, so therefore I need the angle where cosine is equal to root 3 over 2 in the fourth quadrant, because I have a positive x, negative y, and that's going to be 11 pi over 6. So then just plugging that in, I end up with z to be 2 times the quantity cosine 11 pi over 6 plus I sine 11 pi over 6. And then from the previous slide, we talked about that magnitude of z is equal to the square root of x squared plus y squared, which is the same thing as the radius. And we already found the radius to be 2, so therefore the magnitude of z is going to be 2. So now we have one that is in polar form. Z equals 2 times the quantity cosine 30 degrees plus I sine 30 degrees. And so we want to plot this just like we plot in the rectangular complex plane. Similar idea, you just make an r theta point and plot that in the complex polar plane, and then change it into rectangular form and find the magnitude or the modulus of z. So go ahead and pause the video and try that. So if I want this, I'm going to rewrite this just as the coordinate point 2, 30 degrees, and then I'm going to graph that. 30 degrees is the same thing as pi over 6, and I went out a radius of 2 with each ring being 0.5. So now if you haven't already done so, we have this written in polar form. Just convert this point into rectangular form. Converting from polar complex form back to rectangular is actually a little bit easier because I just evaluate the expression. So the cosine of 30 degrees is root 3 over 2, the sine of 30 degrees is 1/2, and then I just distribute the 2 through, so I end up with z to be root 3 plus I. And then the magnitude or the modulus of z is the same thing as the radius, so that's just going to be equal to 2. Just like in rectangular form, we can do different types of algebra and arithmetic with complex numbers. We can multiply them, add them, so on and so forth. So same thing with complex numbers when they're in polar form. So if we have two different complex numbers, we can multiply them together. The way that you multiply them together is you multiply the radii together and add the angles. If you divide them, you divide the radii in that order and subtract the angles in that order. So given these two complex numbers, z equals 3 times cosine 20 degrees plus I sine 20 degrees, and w equals 5 cosine 100 degrees plus I sine 100 degrees, find z times w. So if I multiply them together, I'm going to multiply the radii together, so 3 times 5 is 15, and then I'm going to add the angles. 20 plus 100 is 120 degrees. So when you multiply the radii, add the angles. When you divide the radii, subtract the angles. So DeMoivre's theorem. What DeMoivre's theorem says is that if you raise a complex number in polar form to a power, it fits this rule. This comes straight from our multiplication rule because raising something to a power is just repeated multiplication. So if I raise something to the nth power, that means I'm going to multiply r by itself n times, so that's the same thing as r to the n power. And then I'm going to add theta by itself n times, so that's the same thing as n times theta. So if I'm given a complex number in polar form, I can raise that to a power by raising the radius to that power and multiplying the angle by whatever that number is. So we want to raise 1 plus I to the 5th power, and we're going to do that by using DeMoivre's theorem. So the first thing that we're going to do is we want to convert 1 plus I into complex because it needs to be in complex form first. So go ahead and pause the video and convert 1 plus I into complex. So 1 plus I is the same thing as the 0.11, so I used that and I converted it into polar form. So my radius is the square root of 1 squared plus 1 squared, which is the square root of 2. And then this is in the first quadrant, so I kept that in mind when I found the angle. Sine would be y over r, so 1 over root 2, which is the same thing as root 2 over 2. And since it's in the first quadrant, that means that theta is going to be pi over 4. So the complex version of z is going to be root 2 times cosine pi over 4 plus I sine pi over 4. Now we want to take this whole thing and we want to raise it to the 5th power. So apply DeMoivre's theorem and raise this to the 5th power. So to raise this thing to the 5th power, I'm going to raise the radius to the 5th power, so root 2 to the 5th power is 4 root 2, and then I'm going to multiply my angle pi over 4 by 5, so my new angle ends up being 5 pi over 4. But the last step is they want us to convert this into rectangular form, so from here, go ahead and pause the video and convert this back into rectangular form. So cosine of 5 pi over 4 is negative root 2 over 2. Sine of 5 pi over 4 is also negative root 2 over 2. If I multiply 4 root 2 in, the 4 cancels with the 2's in the denominators. I'm left with 2 over. And so 2 root 2 times negative root 2 is negative 4. And then the same thing here. So you end up with negative 4 minus 4i. So 1 plus I to the 5th power is negative 4 minus 4i. So DeMoivre's theorem, you are getting bigger. You're raising to a power, so both your radius and your angle get bigger. repeated multiplication, so I raise my radius to the same power, repeated addition, so my angle gets multiplied by that power. The complex roots theorem is going to go the other direction. So if I'm given z equals r cosine theta plus I sine theta, and I want to find the nth roots of it, then the nth roots are going to be the same thing. I'm going to take the nth root of r. Whatever I'm doing to z, I'm going to do the same thing to r. But the angle is a little bit more complex. I'm going to take my angle, and I'm going to add 2 pi k to it, and divide by n, where n is whatever root I'm taking, and k is going to start at 0 and increase by 1 until I get 1 less than n. So whenever you take roots, remember there's as many solutions as whatever root you're taking. So if you're taking the third root, you would have 3 solutions. So you would do this with k to be 0, you would do this with k to be 1, and you would do this with k to be 2, and those are your 3 solutions. So for example, if we want to find the cube roots of negative 1 plus I root 3, the first thing that we need to do is put this into polar form. So convert this into polar form. So I used r squared equals x squared plus y squared and got r to be 2, and I used that cosine of theta is equal to x over r, or negative 1 over 2. I know it's in the second quadrant because I have a negative x and a positive y, so then my angle is going to be 2 pi over 3. So negative 1 plus I root 3 in polar form would be 2 cosine 2 pi over 3 plus I sine 2 pi over 3. So now we want to find the cube roots of this. So since we're doing cube roots, that means that n is equal to 3. We're finding the third roots. So we are going to have 3 answers. The first one, we're going to start with k equals 0. So I'm going to apply the complex roots theorem. N is going to be 3, and k is going to be 0. So I plugged in n to be 3, r to be 2, theta to be 2 pi over 3, and k to be 0. Well, anything times 0 is 0, so that goes away. Here I did a little shorthand, the cis notation. Instead of having to write cosine of something and then I sine of the exact same thing, sometimes in shorthand we just write CIS to represent cosine, I, sine. So it's just a little shorthand when you're doing the work because the insides are the same. And then I divided this thing by 3. So anything times 0 is 0, so that part goes away. So inside the angle, I just end up with 2 pi over 3 divided by 3. So then I get the cube root of 2 times cosine of 2 pi over 9 plus I sine of the same thing. That's my first solution. For my second solution, I'm going to do the same thing, but now k is equal to 1, which basically makes this be 2k, takes me around the circle. So go ahead and pause the video and do the same thing, but for k equals 1. So the second solution, I'm going to leave this first part the same because I'm still taking the cube root of 2. And then I'm going to take cosine I sine of my same angle theta, 2 pi over 3, plus 2 pi, and then this time I'm going to multiply by 1 and divide all of that by 3. So what we're doing is we're basically going one more time around the circle, but since we're dividing it by 3, it's really like a third of the way around the circle. So 2 pi plus 2 pi over 3 is the same thing as 8 pi over 3. So I end up with the cube root of 2 times the cosine of 8 pi over 9 plus I sine of the same thing. So that is my second solution. That's my second root. So go ahead and pause the video and find the third root. So now we're going to do the exact same thing, but k is going to be 2. So you end up with 2 pi times 2 up here. So if I simplify the numerator, 2 pi over 3 plus 4 pi would be 14 pi over 3, divided by 3 would be 14 pi over 9. So my third solution, or my third root, would be the cube root of 2 times the cosine of 14 pi over 9 plus I sine of the same thing. So if I take the cube root of negative 1 plus I root 3, I should have 3 solutions, and in polar form, these are the 3 solutions. In this case, it wouldn't be very nice to put this back into rectangular form. You would just end up with a bunch of decimals. You totally could, but nothing would nicely cancel. They're not unit circle points, so you would just have to use your calculator for that. So we can even use this to help us find solutions to something like this, where we have z cubed is equal to negative 8. So in order to solve this, I would want to cube root both sides. So I would get z is equal to the cube root of negative 8, which we know one of those solutions because it's an integer, but there are actually two other imaginary solutions as well, because you have to have as many solutions as there are whatever the power is. So that's what we want to find. So the first thing that we need to do is we need to convert z cubed equals -8 into complex polar form. So pause the video and convert -8 into polar form. So if it's -8, that's the same thing as -8 plus 0i, so x is -8 and y is 0. So I found the radius r squared is equal to x squared plus y squared, so r is just a +8. And then if y is 0, that means that sine is 0. This is a negative x, so that means it's going to be in the negative x direction, so that means theta is going to be pi. So the polar version of this complex number would be z cubed equals 8 times cosine of pi plus I sine of pi. So now apply the complex roots theorem and find all three complex roots and simplify them back into rectangular form. Applying the complex roots theorem, n is 3 because I'm taking the cube root. Theta is the angle that we just found, pi. R is the radius we just found, 8. K starts at 0. So I plug in all of that information. I get the cube root of 8 times cosine I sine of pi plus 2 pi times 0 all over 3. Well, anything times 0 is 0, so that's just going to go away. And I end up with just a pi over 3 inside. And since this is something that's nice on the unit circle, I'm going to convert this back into rectangular form. So the cosine of pi over 3 is 1/2. The sine of pi over 3 is root 3 over 2. So the first solution to this equation is 1 plus I root 3. So now go ahead and pause the video and do the next solution if you haven't already done so. So same thing, except for this time k is 1, so I get pi plus 2 pi times 1 over 3, which ends up being 3 pi over 3. So we get 2 times the cosine of pi plus I sine of the same thing. And if I evaluate this, well, cosine of pi is -1, sine of pi is 0, so this actually ends up being the -2, the solution, the real solution that we already knew. So now if you haven't already done so, go ahead and pause the video and find the third solution. So I'm going to do the whole thing again, except for this time k is equal to 2. And so you end up with pi plus 2 pi times 2, which is 5 pi divided by 3. And then evaluate this because it's on the unit circle to put it back in rectangular form. Cosine of 5 pi over 3 is 1/2. Sine of 5 pi over 3 is negative root 3 over 2. Distribute the 2, you end up with 1 minus I root 3. Which makes sense because we talked about the fact that complex numbers always have to come in conjugate pairs when we were solving these back in chapter 4. So if I have 1 plus I root 3, I have to have 1 minus I root 3. So this section has been the complex plane in polar form, and specifically looking at DeMoivre's theorem. So when you raise a complex number to a power, you raise the radius to that power and multiply the angle by that power as well. Everything's getting bigger. If you are taking complex roots, you're going to have as many solutions as whatever root you're taking. You take the root of that radius, and then theta plus 2 pi k over n, where k increases from 0 up to n minus 1.